Hi, so today we will learn electrical power and energy. So for electrical power, let me explain you one concept. Suppose some current is flowing through a resistor from point A to point B. Current I is flowing and resistor is R. So obviously you can see that current is flowing from point A to point B. So obviously potential at point A will be, if it is VA and VV at point B, then VA must be greater than VB. Okay. Now potential energy of, if a charge del Q is flowing, if a charge Q is flowing in time t, then potential energy of that very charge at point A will be equal to, we know that it will be equal to Q coulomb V volt VA, and at B it will be equal to Q into VB. So what is the difference of potential energy? Therefore, difference of potential energy must be equal to potential energy PE at B minus PE at A, and this will be equal to your QVB minus QVA, and this is equal to Q into VB minus VA. But this is negative because A is greater, so this comes negative. Therefore, del PE is equal to some minus value. Minus of what? Minus of VA minus VB. And we also know that energy is conserved quantity. Energy is conserved quantity means total energy is equal to kinetic energy plus potential energy. It implies that change in potential energy plus change in kinetic energy must be equal to 0. And so, change in kinetic energy, change in potential energy, you have change in potential energy is given by minus of Q VA minus VB plus change in kinetic energy is equal to 0, and therefore change in kinetic energy is equal to QVA minus VB, and this is a positive quantity. So when an electron flows in any circuit, electron is flowing. So if it is accelerated, then it will gain, the accelerated electron will gain change in kinetic energy, which is equal to Q into VA minus VB, Q del V. Okay. But electron does not accelerate. Actually, electron moves with drift velocity. There is drift velocity of electron due to collision with lattice. Electron, though it is accelerated each time, but it collides with the lattice of any material. So there is drift velocity of electron due to electron collides with the molecules, with the lattice of any material, lattice of atom, due to electrons collide with the lattice of atom. And what is drift velocity? This is actually uniform velocity. Drift velocity is okay. So when it collides, while colliding, due to collision, the mean kinetic energy of the molecule is increased. Kinetic energy of the molecules is increased, and this is called temperature, means temperature increased. And thus heat energy is increased. So we are learning first of all electrical energy. So this electrical energy goes into heat energy. Means the electrical energy goes to heat energy. Therefore, heat energy must be equal to change in kinetic energy, which would be in the absence of any hindrance, which would be in the absence of any hindrance. Okay. Therefore, heat energy is equal to Q del V. And you can also say, if you convert the form, this is equal to Q into, in place of V you can write I into R, and in place of Q, charge, you know that charge is equal to IT. So IT into IR, and this is equal to I square RT. heat evolved is equal to I square RT, and this is called Joule's law of heating. Joule's law of heating. So when current passes through any resistor R, this is called Joule's law of heating. When I current passes through any resistor R, any resistor R, for time t, then as per Joule's law of heating, heat evolved is directly proportional to square of current. You can see square of current square. It is proportional to resistance, and it is proportional to the time for which the current is flowing. So this was about electrical energy. Now electrical power. Electrical power. Electrical power. In any electrical circuit, we see that the energy is supplied by any electrical cell or any electrical battery. The energy stored in any electrical cell is that of chemical nature. Chemical energy is stored in any cell. Now, rate of dissipation of chemical energy stored in any cell, which is connected in an electrical circuit, is called electrical power. In another way, you can also say that the rate at which electrical energy is changed into other form like heat energy at any resistance in any circuit is called electrical power. So the rate of dissipation of electrical energy at any device, at any resistance, any electrical device, or resistance in the form of heat or other form. Is called power. It implies that if power is P, power P is dissipated in a resistance R when I current is flowing for time t, then power is equal to rate of dissipation of energy, and energy is equal to energy per unit time, and energy is equal to I square RT, and this is from Joule's law of heating upon time. So power comes equal to I square R. You can convert it in terms of potential voltage also. So from Ohm's law, you can convert I into V upon R. So it becomes V square upon R square into R. So power can also be written as V square by R. Now next thing, in terms of I and V, so from Ohm's law, when you replace this R and change it in the form of I and V, power is changed into, in place of R we'll be writing V upon I. So finally we have three equations of power. Here we got power is equal to IV. Okay, energy of unit of energy I have missed, so let me write here the unit of energy, then unit of power also. So let me take some space. Okay, here I am writing only unit of energy. SI unit of energy is equal to Joule. And heat energy can also be written as calorie. SI unit of heat energy is equal to, and we know that 1 joule is equal to 0.24 calorie. So this is the SI unit of energy and SI unit of heat energy. Now energy of power. Energy of commercial unit of energy. Commercial unit of 1 kilowatt hour, and this is also called board of trade unit, BOT unit. Commercial unit of energy, either 1 kilowatt hour, or you can say BOT means board of trade unit. Now let me convert and define commercial unit of energy. Seeing here, you can observe that when any device of watt is 1000 watt, some motors are there of 1000 watt, some more devices are there of 1000 watt. You have some devices which consumes high power, like motor, like fridge is of 1000 watt. So if a device of 1000 watt, kilo means 1000, if a device of 1000 watt is used for 1 hour, then the energy consumed is equal to 1 kilowatt hour. When a device of 1000 watt 1000 watt is used for 1000 watt is used for 1 hour. Then the energy consumed in the device is called 1 kilowatt hour or 1 baud, board of trade unit. And let me convert this 1 kilowatt hour in SI unit, means in joule. This energy can be converted into joule also. So conversion in SI unit. So we purchase and we sell unit commercially in this unit, not in the unit of joule. Joule is a small unit. We need a large unit for commercially selling electrical energy. So 1 kilowatt hour is equal to, for kilo you can write 1000, for watt is already your SI unit, but hour is not your SI unit. So let us convert hour into second, 60 into 60 second. So now you have watt SI unit, second SI unit. So watt second is equal to joule. You can write now joule. And this is your 36 into 10 to power 5. And this is equal to 3.6 into 10 to power 6 joule. So 1 kilowatt hour is equal to 3.6 into 10 power 6 joule. Some conversion of units will be there, you will do. Now power, SI unit of power. Since so it is equal to watt, and we also know that power is equal to work per unit time, and for work we have unit joule, as energy is capacity to do work. So work will have same unit as the unit of energy. So for work we will write joule per unit time, for time we will be writing second. This is also SI unit of power, watt or joule per second. And there is supply of electrical power from large distances. You know, we have thermal power plants, hydel power plants at very large distances, and from thousands of kilometers away from power stations, we have power supply at our cities, and here we have to consume the power. So we need to reduce the power loss in the path itself. So power consumed by transmission line will be, if PT, then this PT will be equal to I square, and if resistance of transmission line is RT, then PT will be equal to I square RT. Now if voltage across the terminals is V and total power is P, total power is P. Now P is total power, V is equal to voltage across transmission line, then power consumed in transmission line can be written by, since we know that P is equal to IV, therefore in place of I we can write P square upon V square into RT. So we converted I into this form because we are to ensure that the power supplied by our transmission station should not be reduced a little. So I converted I in this term. Power should remain constant. Power should not be changed. So I converted the equation from I square R to P square upon V square into R of resistance of transmission line. Now, the power consumed by transmission line will be reduced if voltage is very high, if denominator is very high. So, power consumed by transmission line can be reduced by keeping voltage very high. Keeping voltage very high. So we have 36,000 volt in transmission lines and they are very risky. Always there is mentioned some caution on some plate. So voltage of transmission lines are, voltage of transmission line is 36,000 volt of this order. So this kind of lines are running all along the path just outside our cities and they are very dangerous. We should be very cautious while crossing those transmission lines. Their voltage are as high as 36,000 volt or near to this. So this was about electrical energy and then power. Now let us do some questions. One question I am doing: what will be the power of some bulbs connected in series in terms of the power shown on bulb itself? You know that on bulb power is written like 100 watt, 60 volt. What is this? This is power. Power is written on the bulb. Suppose on one bulb power is written P1 and voltage is written V1. And you have three bulbs, P2, V2, and third bulb P3, V3. And accordingly they have resistance, they are offering resistance R1, R2 and R3. So when the three bulbs are connected in series, what will be equivalent power consumed by these three bulbs? Equivalent power P consumed by these three bulbs connected in series. in terms of their power ratings. Terms of and which will glow with more illuminance. And means which is more bright. All the three are connected in series. One bulb, two bulb and three bulb. All the three connected in series with mentioned ratings P1, V1, P2, V2, P3, V3. Okay, resistances are not mentioned and we have to obtain equivalent power consumption in terms of these quantities only which are mentioned on bulb. Since we know that equivalent resistance are equivalent in series, is equal to R1 plus R2 plus R3, and we also know that in series your current is same. So let me write in terms of current. P is equal to I square R. Therefore in 1. Therefore in 1, in place of R equivalent, we have to write in terms of V mentioned. Okay, we have to write in terms of V mentioned. So let me change this. We also know that power is equal to V square upon R. It implies that R is equal to V square upon P. So in place of R, we will be writing all these things. Therefore, in 1, equivalent potential is V if all the bulbs are similar and they are showing the same potential V itself, then we have V upon P, V square upon P is equal to V square upon P1 plus V square upon P2 plus V square upon P3, and it implies that 1 upon P is equal to 1 upon P1 plus 1 upon P2 plus 1 upon P3. Now for brightness of the bulb. In terms of power ratings shown on bulb, here you have power ratings shown on bulb if they have same potential drops. In terms of power rating shown on bulbs, if are operated on same potential drops. and same voltage shown. Okay, since we know that power is equal to V squared upon R, so it implies that power is inversely proportional to R. Now when the bulbs are in series, then same current is flowing, and the current is equal to I is equal to V upon R1 plus R2 plus R3, and that is equal to I. Same current is flowing. Therefore, power consumed by one bulb P1, we can write it is equal to I square R. We need to keep this term constant and we need to write power consumed by one bulb in terms of resistance of that bulb. And this I is constant, I is constant because the bulbs are connected in series. This I is constant. Now let us see how power consumed at one bulb is related to resistance. Since resistance is not mentioned, the mentioned thing is power only, so we'll find the resistance in terms of power, and resistance is inversely proportional to power mentioned. So this will be equal to your I square V mentioned, V rated, V square upon P rated. Okay, so power consumed will be inversely proportional to power rated. So smaller is the power rating, more illuminance will be there. Smaller is the power rating of a bulb in series, more illuminance. Power consumed means illuminance. So smaller is the power rating of the bulb in series, more illuminance is there. So when you connect so many bulbs of 40 watt, 60 watt, 100 watt, and you will find that 40 watt bulb is glowing with more power. Now when the bulbs are connected in parallel with rating P1 V1, P2 V2, P3 V3, here you can see all are connected in parallel. So in a parallel combination from Ohm's law, 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Now when you multiply both the sides with V square, you will get this, and it implies that P equivalent is equal to P1 plus P2 plus P3. So power is added in parallel combination, you can see. If you have n bulbs with power rating P each, then power consumed, equivalent power consumed will be equal to P plus P plus up to n times, and this is equal to np. So in equivalent, the equivalent power in parallel combination, you can see that is more than when they are connected in series. Now, what is illuminance of one bulb? Illuminance मतलब power consumed at one bulb is equal to, power is equal to V square upon R1. But we know what the R1 is. R1 we have learnt. R1 is equal to, from this formula, P is equal to V square upon R1. It implies that R is inversely proportional to P. R is inversely proportional to P. So you could see from this one that power of illuminance of a bulb, P illuminance of bulb, okay, one bulb or any bulb is proportional to power consumed, power rating, okay, power rating of the bulb. So more the power rating, more the illuminance will be. If you have suppose 40 watt bulb, 60 watt bulb, 100 watt bulb, then power will be more, brightness will be more, illuminance will be more on 100 watt bulb. So more power rating, more illuminance, more brightness of the bulb in parallel. So when they will be connected in series, then you will see that the brightness of less power rating bulb will be more, and in parallel you will see that brightness of higher power rating of bulb will be more.